Hey, I'm Simeon. JWST just directly photographed the closest Jupiter-like planet ever studied in detail. It's only 12 light years away, and what it found inside that planet's atmosphere breaks every model scientists have built to understand worlds like this. The models didn't predict it, and the implications reach well beyond this one planet. Almost every exoplanet atmosphere JWST has studied in detail belongs to a world that is scorching hot. That's not a coincidence. It's a limitation of the most common detection method. To study an atmosphere, scientists need a planet that passes in front of its star from Earth's perspective. Planets that do this reliably tend to orbit very close to their stars. Close orbits mean extreme heat. Jupiter sits 5 times further from the Sun than Earth. Its cloud tops hover around minus 145 degrees Celsius. It's cold, distant, and complex. And until very recently, studying a planet genuinely similar to it around another star was essentially impossible. The instruments didn't exist, and the techniques weren't sensitive enough. JWST changed this by making direct imaging of cold, distant planets possible for the first time. Instead of waiting for a planet to pass in front of its star, direct imaging blocks out the star's light entirely, using a coronagraph, allowing the much fainter planet to be seen directly. It's technically demanding and requires the most sensitive infrared instruments ever built. But it opens a window onto planets that look nothing like the hot worlds that dominate most exoplanet research. Planets that actually resemble the gas giants in our own solar system. Epsilon Indi Ab was one of the first targets. The planet orbits a star called Epsilon Indi A in the southern constellation Indus, just 12 light years away from Earth, making it one of the closest planetary systems we know of. The planet itself is a super Jupiter. Its mass is 7.6 times that of Jupiter, but its diameter is almost identical. It sits roughly 4 times further from its star than Jupiter sits from the Sun. A genuinely cold, distant world with surface temperatures hovering between minus 70 and plus 20 degrees Celsius. Cold enough for ice to form. Cold enough to be a real analog to the gas giants in our own solar system. JWST first imaged Epsilon Indi Ab in 2024. That observation confirmed the planet's existence and gave scientists an initial look at its chemistry. The new study, published April 2026 in the Astrophysical Journal Letters, is the second visit, and the results from that second look are what nobody expected. The models had a clear prediction. A planet with Epsilon Indi Ab's mass and temperature should have large amounts of ammonia gas in its upper atmosphere. Jupiter does. The models for cold gas giants consistently predicted. The team went in expecting to confirm that prediction. What JWST found was different. The ammonia levels were significantly lower than any model had calculated. Not slightly off, but meaningfully, unexpectedly low. The team ran the numbers multiple ways. The shortfall was real. The missing ammonia isn't absent, it's hidden. Thick, patchy clouds of water ice are sitting in the upper atmosphere of the planet, blocking the ammonia signal from reaching JWST's instruments. The clouds are acting like a veil, obscuring what lies beneath them. Water ice clouds on a planet 12 light years away, detected for the first time on any world beyond our own solar system. The clouds themselves are similar in structure to cirrus clouds on Earth, the thin, high-altitude ice clouds that form at the top of Earth's atmosphere. Except on Epsilon Indi Ab, they are thick and patchy, spread unevenly across the planet's upper layers in ways that directly affect what instruments can detect from across 12 light years of space. Lead researcher Elizabeth Matthews at the Max Planck Institute for Astronomy put it directly. JWST is finally allowing scientists to study solar system analog planets in detail. If we were aliens several light years away looking back at our sun, JWST would be the first telescope capable of studying Jupiter this way. Every atmospheric model scientists used to interpret exoplanet observations was built around a simplification. Clouds were left out. Not because scientists didn't know clouds could exist, but because including them makes the computation dramatically more complex. It's easier to build a model without clouds and accept that it's an approximation. For hot planets close to their stars, that approximation holds reasonably well. Hot atmospheres are too energetic for certain types of cloud to persist. The simplification doesn't cost much. For cold planets like Epsilon Indi Ab, worlds with temperatures close to Jupiter's, clouds are not a minor correction. They are a fundamental feature of the atmosphere. Leaving them out doesn't produce an approximation. It produces a wrong answer. Every cold gas giant among the thousands of confirmed exoplanets may have been mischaracterized by the models that ignored cloud layers entirely. Co-author James Mank from the University of Texas described it as a great problem to have. What once seemed impossible to detect is now within reach, revealing layers of complexity the models are only beginning to capture. Matthews and her team are already applying for more JWST observation time to study additional cold Jupiter analogs. The goal is to find out whether Epsilon Indi Ab is unusual, or whether water ice clouds are a standard feature of cold gas giants that every previous model simply missed. 12 light-years away, a planet similar in size to Jupiter is wrapped in clouds of water ice that our best models never predicted. JWST found them. Whether this is a quirk of one unusual world or a gap in our understanding that runs across thousands of planets is the question this discovery leaves open. If you liked the video, please give it a thumbs up and subscribe for more videos like this one. Thanks for watching, and I'll see you in the next one.